So, ladies and gentlemen, here we go. All right. Chapter 11 is on the topic of solutions, okay? And a good amount of it is going to be review from your Chem 1, which is always very nice.
That's not.
Okay, so there is some math in this chapter, but it's math that you did in Chem 1. It's easy stuff, okay? And the rest of the chapter is concepts, but again, it's concepts you've learned before. And the thing that I love about this chapter is it's got a lot of real life application. It's got a lot of interesting stories that we can share in here. It's one of my favorite chapters, okay? So, please tell me, let's start off right off the bat here. The word solution. Can you give me another term that is a synonym for the word solution? Someone, not compound. What type of mixture? Homogeneous mixture. Okay? A homogeneous mixture. Okay? And, guys, I want you to be aware that although most of the time, when we talk about solutions or mixtures, we're almost always talking about a solid being dissolved in a liquid. And usually that liquid is water. However, I want you to be aware that you can have any phase, solid, liquid, gas, dissolved in any other phase. Okay? Just because we talk about solid and liquid a lot doesn't mean that that's not the only thing that exists out there. For example, soda water, seltzer water, club soda, whatever you want to call it. What is that? Okay, a gas dissolved in a liquid. What gas is it? What is it? Carbon dioxide. Okay? That is a gas dissolved in a liquid. Let me give you another example. I think this one is so neat. It's an example of a solid dissolved in a gas. It's not impossible. A solid dissolved in a gas.
Airbrush.
You're close. Smoke. Smoke. He said dust. No, not toothpaste. Okay? Smoke is essentially minute particles of ash dissolved in air. Okay? So you can have any phase dissolved in any other phase. Ladies and gentlemen, we are, however, going to focus on aqueous solutions. Please remind me what that word means. Water is the solvent. What's the other part of this equation? Solvent and solute. Okay? Now, what we're going to start off with, the only math that we're going to deal with in this chapter is different ways to calculate a solution's concentration, okay? And these are the three that we're going to see the most often. This, I put molarity first because it is definitely the most common of the three, okay? You'll notice on the list of problems for the Chapter 11 problem set, there's a couple of places where it says ignore molality, okay? Molality is another way to calculate a solution concentration, not on the AP exam anymore. So, okay, these are the three we're going to focus on. Let me refresh your memory on how to calculate these, okay? Molarity, moles of solute divided by liters of solution. Another way to say this denominator would be total volume in liters. Okay? Remember that you can write the units for molarity either with a capital M or what's the other way that's okay to write it? The units. Moles over liters. Okay? All right, you could also calculate a percent by mass, meaning grams. mass of solute divided by total mass of the whole solution times 100. Okay, so it's a percentage. Or you could be asked to calculate a mole fraction. Okay, and a mole fraction, what's in the numerator, could be the moles of either part of this solution. You could have the moles of the solute or the moles of the solvent. It depends on what they ask for. But moles of some part divided by total moles. What would be the units for this last one? Unitless. Moles cancel out. Mole fraction, and this term is, guys, kind of a misnomer. Don't ever leave something as a fraction. We don't do fractions in chemistry. Divide the numbers out. A mole fraction should be a decimal number, but it has no units.
And what's that?
That's, that's the variable for mole fraction, okay? That's just how it's represented, like little m means mass. Capital X stands for mole fraction. It's not its unit, it's the variable for it. Okay. So I'm going to have you do 2 practice problems with this, but before you start reading or anything like that, okay, I want to give you a little bit of advice, all right? The first problem here is very, very straightforward, very easy, definitely Chem 1 level problem. The second one is more like what you will see, okay, in the future. And I just want to give you a couple of tips, and then I'm going to stop talking. When I say that the second problem is more typical of what you will see, what I mean is you will be given one type of solution concentration. Like in this example, you're given a mass percentage, and I want you to change that into the other types of solution concentration. My suggestion to you, since this is more like what you'll usually see, whatever type of concentration you are given, set it up like a fraction. Okay, so for example, a mass percentage, I'm going to rewrite that as 38 grams of solute over 100 grams of total solution. Anytime I write that, by the way, SOL apostrophe N, that just is shorthand for solution. Okay? Write it out like that. Let's say in a different problem, you were given a molarity, for example. And the problem gave you a molarity and then said, calculate the mass percent and the mole fraction. Like, let's say you were given a concentration of 4.5 molar. Rewrite this like this. 4.5 moles of solute over what? 1 liter of solution. Okay? You certainly don't have to do this. I think, however, you will find it helpful when you can take whatever piece of information is given to you and rewrite it a little bit differently. It just helps you figure out how to get to the other pieces that you're asked to solve for. Okay? So that's just my piece of advice. Take it for what it's worth. Try these, please. Go. Do you all remember a cubic centimeter is equal to what unit of volume? A milliliter. To get a mole fraction, I'm going to have to figure out how much solvent I have. First of all, what is the solvent? How'd you know that? Because it said aqueous, okay? How can I find out how much just water there is here? Look at the first piece of information I wrote down. 100 minus 38 will give me the mass of water, which I can then change into moles. Okay, so guys, number one was basically just a warm-up to get you back in gear of calculating concentrations, but number two is more like what you will see, okay, where you are given some type of concentration and asked to change that one into other types of concentration. Okay, again, my advice is whatever your given piece of information is, set it up as a fraction and then take it piece by piece from there. Okay? All right, moving on. So, before we get to some of the more interesting everyday life stories kind of part of this chapter, I need you to understand what is physically occurring when one thing dissolves in something else. It's actually a very violent process, okay? There are things being ripped apart. And it basically occurs in 3 steps, okay? And we're not going to do any energy calculations, but we are going to talk about in just a second the energy associated with each of these 3 steps. Okay, but for now, let's just talk about them, okay? If you are trying to dissolve, let's use a really easy example. Salt in water. NaCl in water. The first thing that has to happen is this is actually too nice a word, expanding the solute. Let's call it breaking the solute apart. Think about it. If a solute dissolves, doesn't it break apart? Say yes.
Yes.
Okay. So you've got to break apart the solute. You've also got to expand the solvent particles. Okay, now I don't mean completely break the solvent apart, but if solute particles are going to get into this solvent, the solvent particles have got to pull away from each other a little bit. They've got to make room. So that's step 2. And step 3 is the one that we're really going to focus on. And this is the step that really decides whether something will dissolve in something else or not. It's how do the solute and solvent interact with each other? Are they attracted to each other or do they repel each other? Is is essentially the question. Okay? Again, we're not going to do any calculation with this, okay? But there is a heat associated with each step. And we'll talk about those heats in just a second. Okay? And as I said, that third step is really the crucial step. And before I talk about this, I want to refresh your memory about this phrase. Did you ever hear this in Chem 1? Like dissolves like. What does it mean? Polarity. Polar solvents will dissolve polar solutes only. Nonpolar solvents will dissolve nonpolar solutes only. Okay? And guys, when I say like a polar solute, that includes ionic solutes as well. Okay? Would you agree that table salt is ionic? Okay? So salt will dissolve in water, okay, because they both have polarity to them. What about something like oil? Is oil polar or non-polar? Polar. Non-polar. If you put a whole bunch of salt in a pan of oil, is it going to dissolve? Nope. Why? Because of a difference in polarity. Okay. But if you took something like, and this is really gross, but I'm from the South and in a lot of Southern cooking involves cooking with lard. Pure animal fat. Okay? All right? I agree. What's not to love? It makes everything taste better. But I know I'm in the minority on that one. Okay? But if you had a pan of oil on the stove and you took solid pieces of lard, which is also non-polar, it would dissolve beautifully. Okay? A non-polar will dissolve another non-polar. And guys, we're going to talk about this some more. It's all to do with the interaction between solute and solvent. Okay? Now, if the heat of that solution is very, very negative, what does it mean for an energy value to be negative? Exothermic. Think way, way back. Exothermic reactions, are they typically spontaneous or not spontaneous? Spontaneous, usually. Not always, but usually. If your heat of solution is very, very negative, when I say go, what I mean is the solute will dissolve in the solvent. Okay? It means that's a very favorable reaction. If your heat of solution is very, very positive, which means not exo, but endo, when I say no-go, that means no. That solute is not going to dissolve in that solvent. Okay? And it's all to do with energy. Right? If, however, your heat of solution is positive, but not very positive, okay, so it is endo, but not very endo, usually you will still get the dissolving process to happen because of this. Do you remember what that word means? Chaos, disorder, messiness. Okay? Think about it. If I have a sample of salt over here and a sample of water over here, separate, or I have them mixed, which situation is messier? When they're mixed. Okay? Does the universe like it for things to be messy? Yes. Okay? Things that are messy are typically favorable reactions. So if the heat of that solution is positive but not very, very positive, usually the dissolving process will happen because the increase in disorder favors it. Okay? But if it's large and positive, no, that's not going to happen. Yes?
How do we discern between small and large?
I would not give you a single number and say, is this small or large, but I could give you two. Like, this is the delta H solution of one is 3 kilojoules per mole, and another one is 30,000 kilojoules per mole. This one will happen more favorably than that one. I'd have to give you two numbers to compare. Okay. Now, this is really what I want to focus on before we get into the interesting stuff here. Not that this hasn't been riveting so far. Okay? But, ladies and gentlemen, I again want you to know on a molecular level what is occurring here. And let's use this really simple example, table salt in water. Okay? And I'm going to tie this back to those 3 steps that we talked about. Step 1, if you go back, says expanding the solute, breaking it apart. Ladies and gentlemen, why would energy be required to break this apart? Nope. What kind of bonds am I breaking? Ionic bonds. Are those easy to break?
No.
No. Okay? They are not. Ionic bonds are incredibly strong. To break up this solute will require energy. Isn't that saying that breaking this apart is an endothermic process? True. Yes. Okay? Breaking apart your solute, no matter what, ionic, covalent, no matter what, is always endothermic. What if my solute was not ionic? What if it was a covalent compound? To break a covalent solute apart, what are you breaking? Intermolecular forces. Okay? Are those easier to break than ionic? Yeah, but it still requires energy to break them. Okay? Step 2 says expanding the solvent. Well, in this case, water is the solvent. Here's one water molecule, here's another. I need to pull them apart from each other. What am I breaking? What kind of bonds? Intermolecular forces. Does it require energy to break those? Yes, it does. So step 2 is also endothermic. Step 3 is the way the solute and solvent interact. And I want you to look at these 2 pictures. Let's start with the one on the top. We've busted up the solute. Can you please tell me why would these little Na pluses want to surround themselves with the oxygen side of those water molecules? Okay, somebody said the oxygen side is more negative. You're right. Okay, we're not talking ionic charges here. Why is the oxygen side of this molecule a little bit more negative? Okay, it's a polar molecule and oxygen is more electronegative. Remember, water has that bent shape. And this side is more negative, which means what about this other side? And look at the lower picture. These Cl minuses are surrounding themselves with the hydrogen side of the water. Why are these 2 sides attracting? Opposites attract. Okay? This is what happens. And guys, this is a favorable process. Negatives and positives like to be near each other. This particular example, step 3, would be exothermic. It does not require energy to get this to happen. It's going to happen on its own. So steps 1 and 2, no matter what, always endo. Step 3 will be exo, usually, if something will dissolve. If this process in step 3 is not favorable, meaning it's endo, then it's not going to dissolve. Okay? Like throwing salt into a pan of oil. It's not going to happen because step 3 is not a favorable process. Okay. And we talked about that. Let's move on. All right. So, we're going to talk about the fascinating world of soap. I'm sure you have never thought about it. Okay? But I'm going to just expose my nerdness here. Okay? I think soap is fascinating. I wrote an entire college essay on soap. Okay? Just wait. You too will never wash your hands the same way again. Okay? All right, let me give you a hypothetical situation. For any of you that ever do any cooking in your house, particularly cooking with meat, sorry, vegetarians, okay? If any of you have ever worked with, chicken, or you've made hamburgers or marinating steaks or anything like that, when you've been working with meat, your hands are pretty greasy after you're done. Has that, anyone? Yes. Okay, it's fat, exactly. It's the fat from the meat coming off on your hands. So what do? Before you go and you handle any other food that you're going to be working with, you go over to the sink. If you take your hands and just put them under the water, why? It does nothing. The water just runs right off. And why would that be? Okay, water is polar and fats are, they're not going to interact. So what do? You go over to the soap dispenser. You sing your ABC song twice like you're supposed to, like the little poster in the kids' bathroom says to. Okay? And then you put your hands under the water again, and magically, it's gone, and your hands are back to normal. So what's so special about soap? Well, let's talk about it, shall we? Yes, Rami? Well, why don't you wait and find out? Okay? Ladies and gentlemen, this is essentially what a soap molecule looks like. And I mean any soap. Like hand soap, dishwasher detergent, laundry detergent, even some components of toothpaste, which is essentially a soap. Alright? Soap molecules look like this. They have a head and a long carbon chain tail region. Okay? Here's the deal. Okay? We look at the two portions of soap as two separate pieces. The tail, we use the word hydrophobic. What does the prefix hydro mean? Water, and phobic? Fearing. Water fearing. Why would this tail region not like water? Because it's a very non-polar kind of structure. Long carbon chains, fats, oils, waxes, all have this same kind of carbon chain. The head region, however, has charges on it. Look. Okay? If it's got some negative charges, do you think this will attract to water?
Yes.
Yes, it will. Water loving, hydrophilic. Okay? So the tail region the head region likes to be around water and the tail region doesn't. All right, great. Well, that fancy graphics here, I know, that is a big droplet of fat. Bleh. Okay? That is on your hand because you've just been making hamburgers. All right? The grease is non-polar, water is polar. You put your hands just in the water, it does nothing. No good. Here's what happens. Are you ready? Prepare to be dazzled. What? Okay? Watch. This is so cool. The little soap tails, they come along and they kind of put their little tails, okay, in the little droplet of grease. Okay? And why would the tails like to be near the fat? Non-polar and non-polar like each other. And what happens is these minute little droplets of grease, fat, whatever, have all these little tails embedded in them, and the heads are coating the outside. And the heads like water, don't they? They're hydrophilic, so you put your hands under the water, and the water runs over it and sticks to it and just whoosh, whisks it away. It's magic. Isn't that neat? All to do with polarity. Boy, these graphics are incredible, aren't they? They are really, really incredible. Okay, let's talk about something else. All right? Let's talk, yeah, it was a life-changing experience, wasn't it? Okay? Let's talk about some other real-life things here, okay? Have I mentioned the word at any point today, have I said the word pressure anywhere?
No.
No, I have not. Okay? Ladies and gentlemen, the pressure in a room has zero effect on whether or how much a solid or a liquid will dissolve. But, let's go back to something we mentioned earlier. What if a gas is your solute? Like club soda, seltzer water, whatever you want to call it. If gases are your solutes, then the pressure in the room has a big impact. Okay? Have you ever noticed, if you buy like an unopened bottle of, 2-liter bottle of any kind of soda, somewhere on the label it says contents bottled under pressure. Okay? Applying pressure above the surface of these liquids allows more gas to be dissolved. Why would you want a soda to have a lot of gas dissolved? So it's not flat. It's fizzier. Okay? You want there to be as much gas dissolved as possible. Right? And when there isn't as much, we say that it's flat. Ladies and gentlemen, this is a relationship called Henry's Law. It is a direct relationship. If you increase the pressure above the surface of a liquid like this, like pretend we're at the Coca-Cola bottling company, and we are bottling 2-liter bottles of Coke, they apply a great deal of pressure to get as many carbon dioxide gas particles to dissolve into that soda.
Amazing.
It's a direct relationship. You increase the pressure, you increase the amount of dissolved solute gas. Now read, when you have a brand new bottle of Coke and you open it, what sound do you hear? What is that? What?
Yeah.
There's gas escaping. Where's the gas coming from? The inside. Be more specific. Where's the gas coming? What gas is it, first of all? It's not air. It's CO2.
Carbonating soda? Okay.
You open a brand new Coke, you hear that it's escaping CO2. Where's the CO2 coming from?
The bottle. Inside the bottle.
It's your Coke starting the process of going flat. And read, why would that be? Opening a bottle of something pressurized, you are doing what to the pressure? You're decreasing it. It's the opposite. If you decrease the pressure,
You decrease the salt?
you decrease the amount of dissolved gas. The dissolved gas starts to come out of solution. Okay? That's called Henry's Law. We're not going to do any math with it. Okay? It's just, all I want you to know is that it's a direct relationship. All right, so we've talked about pressure. Ladies and gentlemen, let's talk temperature. Woo! Okay? I want you to focus on the lines in blue, please, on this graph. You saw these in Chem 1. You probably saw literally this exact graph. I mean, there aren't that many solubility graphs out there. Okay? Temperature is on the X. What's on the y-axis is the amount of each of these solutes that you can dissolve. Okay? Real life example, people. You have a sample of tea, and you like sugar in your tea. Okay? You have 1 cup equal volumes of iced tea and 1 of hot tea. Which one can hold more sugar? Which one can dissolve more sugar? The hot tea. As temperature increases, the amount of solute increases also. Let me be clear though, this is an important word. If your solute is a solid. Good question. So let's say you have water at like 60 degrees and you've dissolved this much sugar, and then you start cooling it down. What you get is the sugar that was dissolved starts to come out of solution and just would start to pile up at the bottom of the cup. Like if you take, if you had a sample of hot tea and you dumped a whole bunch of sugar into it and then immediately put it in the refrigerator, over time you would just start to see sugar piling up at the bottom. Okay? So let me just be clear. If your solute is solid, increase the temperature, you increase the solubility. However, again, fancy graphics, I know. Okay? The opposite is true if it's a gaseous solute. Okay? Real life example. Okay? Let's say it's the middle of the summer, right? And you buy an ice cold Coke out of the vending machine. For my money, there is nothing better than like on the hottest day, getting an ice cold, like red classic Coke. None of this Coke Zero business. Just a Coke. There is nothing more refreshing. Tell me, why do we keep sodas in the refrigerator? Besides the fact that we typically like them to be cold, what's the purpose of keeping them in the refrigerator?
They don't go flat.
So they don't go flat. Okay? The colder it is, the more gas will be dissolved. So you buy that ice cold Coke out of the vending machine in the middle of July, and then you accidentally forget about it and you leave it in your car, parked in the parking lot where it's baking. And then you come back from running your errands and you get in the car and you want to go for that, what was an ice cold Coke, is now a hot Coke that is totally flat. Gross. Okay? As temperature increases, the solubility of a gas decreases. Okay? And the reason is chemically, because as the temperature rises, you're giving those gas particles that are dissolved more energy to escape, jump out of solution. Interesting story. All right? Story time. Get comfortable. It's story time. All right? For any of you that are outdoorsy, like you like to go canoeing, camping, hiking, etc., okay? You can, if you go far enough north up the Potomac River, you can take a canoe down the river. If you go far enough north, the Potomac River is not the super duper wide rapids river that we see around our area. It's actually a much smaller river. It's very pleasant. It's very canoeable. That's not a word, but whatever. Okay, so my friend and I rented a canoe and we're canoeing along. And I think it was maybe April, sometime like that. And if you canoe along, so Maryland would be on your left-hand side because we were going south, and Virginia's on the right-hand side. And up on the left-hand side, we see on the Maryland side, there's a nuclear power plant. Okay, no big deal, whatever. So we're canoeing along, and my friend says, put your hand in the water. Okay, fine. It's April, so the water's still, it's kind of cold. It's cold enough you don't want to get in it, all right? But we put our hand in the water, and it was about the temperature of, like, a hot tub. Huh? What? That's weird, okay? And so we're canoeing along, and as we are passing this nuclear power plant, the water is incredibly hot, and then as we go along, it's still warm, but it's getting cooler as we go away from it. Well, ladies and gentlemen, nuclear power plants are typically situated next to some flowing body of water because they pull water from this source and run it through their cooling towers to cool down the nuclear reactors. Now, that water never comes in contact with any kind of, like nuclear material, but it, in the process of running through those cooling towers, gets very, very hot. Okay, and they run the water through the tower and then they put it right back into the river. Okay, it's not nuclear waste water or anything, but it's very, very hot. So who cares? Why should we care? How do fish breathe?
With their mouths.
With their mouths. No, wrong. Okay, but what are they breathing? They're not breathing water. The dissolved oxygen. Now think about that for a second. If your water source, that you're a little fish and you're swimming around, and your water that you're swimming around in is extremely hot, there's no oxygen to breathe. Thermal pollution is killing wildlife or aquatic life because there's no more dissolved oxygen to breathe. So people typically, there's a lot of reasons why people don't like to have nuclear power plants near their homes. This is one of them because it kills a lot of aquatic life. One other little story to share with you. We're still in story time. Okay. There is actually a little box in your textbook somewhere in this chapter that tells the story of the Lake Nyos tragedy. And I saw this whole documentary on it on the National Geographic Channel. Excellent channel, by the way. So there's this lake in Africa. I want to say it's in the country of Kenya. I could be wrong about that. Okay. There is a lake, and there was a village of people who lived around the lake. And overnight, I believe it was overnight, within 30 minutes, this entire village of people died. All of them just dropped. Okay? And these scientists came in to try and figure out what happened because there was like no signs of struggle, there's no signs of any kind of foul play, nothing. Just people, whatever they were doing, just dropped what they were doing and died. And so what they found was, they took video footage of it. These scientists went out on the lake in a canoe, and think about if you've ever been canoeing on a lake, the water is pretty still unless, a boat goes by. But these guys are in a boat and they're filming what the water looks like, and it looks like a hot tub. Like bubbles, like, okay? There's no jets in the lake that are producing these bubbles. So they're like, this is a little odd. A lake should not be bubbling like this. What they figured out was that at the very, very bottom of this lake, pretty deep lake, there is, I think it's called a fissure. It's like a crack in the Earth's crust, okay? And a lot of CO2 gas was coming out of that crack in the Earth. Not a problem because at that very, very deep depth, pressure is high, okay? If you swim, very deep down in water, you start to feel it in your ears. The pressure gets very high. High pressure, you can get quite a bit, dissolved gas is favored, okay? So all this CO2 that's coming out is immediately dissolving once it hits the water. So no big deal. Well, what happens when you take you open a bottle of Coke, or you don't even open it, let's say, and you shake it up? What happens? All of the CO2 comes out, okay? All at once. Well, this lake, you can't shake a lake, but you basically can because there was an earthquake. So the lake is shook up, and all of this CO2 comes racing out of the lake in this giant bubble, And CO2 settles over this entire village and essentially suffocates all these people in a matter of minutes. Okay? They figured this out because, as I understand it, the scientists, as they were getting close to the village, so this lake is still reacting. They're starting to feel, as they get closer and closer to the village, they start to feel dizzy and lightheaded because there's less and less oxygen in the air and there's more and more CO2 in the air. So they had to actually put on oxygen masks. And then they went out on the lake, and obviously they figured out what was going on because they're watching this lake around them bubble like crazy. Okay? And then they took samples and figured out it was CO2 that was bubbling out, and then that's how they figured out what happened. Anyway, agitation also gives gaseous particles energy to escape. Okay? So, let's finish this up. This is our last topic. Okay, you did this in Chem 1. We're not doing any math with it. It is all conceptual. This is a change from last year to this year. Okay, we learned the word volatile last week. What did the word volatile mean in chemistry? Violent, no. More specific, what does it mean? A liquid that, what? Evaporates easily. So if something is non-volatile, does not evaporate easily, okay? It says addition of a non-volatile solute to a solvent affects certain properties. They're called colligative properties, and I'll tell you what the word colligative means in just a second. You see three things happen. So let's make a real easy one. Pure water versus salt water. What's the boiling point of pure water? 100. When you add salt to it, and now it's salt water, it doesn't boil at 100 anymore. Maybe it boils at 105. This is one of the multiple reasons why people salt the water that they put pasta in. If it's cooking at a higher temperature, you can cook your pasta faster. Okay? What temperature does water freeze? Pure water. 0. Salt water might freeze at -7. This is why they put salt on icy roads. Okay? Think about it, guys. If it is exactly 0 degrees Celsius outside, will there be ice on the roads? Yes. There will also be some liquid water, but there will be some ice. They throw salt down on the roads. The salt intermingles with those H2O particles, and now it's not water on the roads anymore. It's salt water. If it's exactly 0 degrees, but salt water doesn't freeze until you get down to -7, it won't be frozen anymore. That's why they salt the roads, in case you didn't know that. Okay? We talked about vapor pressure last week. You also get a decrease in the vapor pressure as well. And I want to show you a picture of why this occurs. Okay? Picture on the left, let's say, is pure water. Picture on the right, salt water. Please count for me, if you would, how many gas particles are in the picture on the left? 9. How many gas particles in the picture on the right? 6. There's less gas when we add salt, and here's physically why. I think this is actually really neat. If you add salt to water, or any solute, that solute forms what's essentially like a screen on the top surface of the water. If you have a screen over something, can things still get in and out? Yes, but it's not as easy. Okay? It's not as easy as it was. Can water still escape into the gas phase? Yes, but it's not as easy as it was before. If you lower the vapor pressure, because there is less gas, that's why the boiling point goes up. So in order to boil this, you have to add more heat over here than you did over here. and that's why. Okay, so it lowers the number of solvent particles at the surface of the water, or the liquid. It lowers the escaping tendency, because those solute particles form essentially like a little screen. Okay, this is our last slide. Here's what the word colligative means. The effect of the added solute only depends, underline it, on the number of solute particles. Does it say anything about the concentration of the solution? Nope. Does it say anything about what type of solute it is? No. What do I mean by number? Well, let's stick with this example. If that solute breaks apart, how many ions do you get? How many pieces do you get? 2. If this were my solute and it fell apart into all of its pieces, how many pieces would you get? How many? Let me ask you another question. How many ions would you get? 4. 1, 2, 3 lithiums and 1 phosphate ion. So 3 plus 1 is 4. What about if this were your solute? You'd get 5. Guess what? This one would have the biggest effect. Okay? If I have 3 cups of water, equal volume, and I put equal amounts of all these 3 solutes, boom, 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 this one's boiling point might be 102, 105, 108. The more pieces there are in the solute, the bigger effect you're going to get. So let's look at this example problem. Which aqueous solution would have the highest boiling point? Well, be careful with this first one. Does anybody remember the formula for glucose? Oh, wow, okay. Does sugar dissolve in water? Yeah. Okay. When it dissolves in water, how many pieces am I going to get? 1. This is not an ionic compound at all. All that's going to be broken when glucose dissolves is intermolecular forces. How many pieces are you going to get with this one? 2. How many pieces with this one? How many pieces? Here's your answer. Ladies and gentlemen, this was taken from an AP exam a couple of years back, maybe. Notice that I didn't even look at these. They don't even matter. They don't matter at all. It's just how many pieces do they fall apart into. I want to say one last thing and then I'm going to stop talking. You need to be very, very careful when you're going back and reviewing chapters 10 and 11, because do you recall in chapter 10 we had a lot of questions like, which compound has the highest boiling point? Which one has the highest melting? Which one has the greatest vapor pressure? Yes, you remember? Guys, those were not solutions. Those were either pure elements or pure compounds. Okay? And for the most of those questions, you needed to answer, what you needed to answer it was, which one has the stronger intermolecular forces? Did we say anything about comparing intermolecular forces here? These are solutions. I didn't say, does glucose, KCl, or this have the highest boiling point? I asked, which solution of these? If it's a solution question, you look at how many pieces there are. So be very, very careful with that.